I work on this project, and together with this team, Dave, Amod, Avery, Adam, Vidya, and Afroza. So first, what is web crawl cache? Well, Yahoo as a search company is crawling the web in order to build its index. As part of the search deal between Yahoo and Microsoft that was signed a while back and is currently in progress, transitioning gradually through the markets, at some point when transition is complete, Microsoft will be providing Yahoo with all this search backend, and it's expected then that Yahoo will stop crawling the web. Since this database of the entire crawled web is very valuable, the deal includes a part whereby Bing, Microsoft Search, will be sending to Yahoo all of its crawled content and associated metadata. So web crawl cache is a tool for mirroring Bing's crawled content in Yahoo. And in order to do that, Microsoft have set up a system on their end, which I'm not going to talk about. And on the Yahoo end, we set up 2 clusters, 960 nodes and 720 nodes. And I'll talk about what they do in this presentation. This is basically the hardware setup. They're running Hadoop. We store multi-petabyte of data, about 2 petabytes, plus the 3x replication, plus a few other associated pieces of data. And we run HBase, which I believe is the largest single HBase setup in the world today. So why even do this? Having a snapshot of the entire web is very valuable. It's valuable both for search, but also for other things as well. Now, for search, while Microsoft will be providing Yahoo with a search backend, Yahoo is continuing to innovate around the front end. So having a full snapshot of the web allows Yahoo to do things like drill deeper into certain verticals, like local content or shopping or research or other such things. And then when you see a query with a specific intent, you can tailor results for users. You can also, since Yahoo has a lot of information about its users, you can tailor results to individual users. Beyond search, you can analyze the web. You can see which sites are big, which sites are important, which topics are trending, which topics are hot, and you can use that to enhance users' experience in all of the other Yahoo properties. You can enhance sports, finance, news, and so on, having this big database. You can also do general research. Having many billion pages in all the languages in the world allows you to do a lot of research around linguistics and all sorts of other interesting issues. So what we set out to do is to efficiently mirror petabytes of data that are changing at web speed. So this isn't just taking a few petabytes of data and copying them once. This is taking petabytes of data where many terabytes change every day. And of course, we wanted to make this data easy to use inside Yahoo for various applications. So from a very high point of view, we have Bing on one side crawling the web. We have web crawl cache in the middle, who is mirroring the contents that Bing has. And then we have data sets that we dump to other grids inside Yahoo. And we have various custom processing that we do on this data. And we also allow to do random reads on this data. A little bit lower level, so we have Bing on one side. On our side, we have this set out. I'm starting from the top left. We have the poller, which schedules things around, and it checks to see if there's any new data set to get. If there is, it launches the fetchers, which go out and get the data. Then it launches an ingester, which reads the data and writes it back in a form that's easily consumable by HBase. HBase picks up these files, loads them into HBase tables, and from there we have scans that run through the data to produce data sets, and we have random reads, and we also have a processing cluster on the side which does some heavy lifting processing on the data. And I'll go into more detail on each of those. So Polar. Polar is basically a fancy scheduler. It polls to see if there is new data available for fetching. If there is, it schedules, it monitors. It's a MapReduce program, but the most trivial one. It's a single map task. And we only use MapReduce actually for its high availability. So we launched this job. If it dies, it's restarted. It's just a fancy job manager. Fetcher, that's on the bottom left over there. Fetches one batch of data. Whenever a batch is available, we launch a MapReduce job with many tasks, each of which goes off and fetches a smaller piece of data from Microsoft. You can look at it as a fancy wget, large distributed wget. A typical job has about 3,000 of these tasks, take about 15 to 20 minutes. Interesting part was to control bandwidth. So the bandwidth between Microsoft's data center and Yahoo's data center is limited and needed to be used in a controlled manner. And we attacked that by configuring queues, Hadoop queues. So we set up queues that will accommodate a specific maximum number of tasks, and then we run our jobs, which have many more tasks, in a constrained queue. And so we know how many tasks we'll be running. In addition, we configured the network such that an individual TCP connection has a limited bandwidth, so we can, in a fairly straightforward way, configure our bandwidth. In case of failures, we retry, and in case there is a network outage or other kind of outage, planned or unplanned maintenance, things like that, then we go into what we call catch-up mode. We have a backup queue where we launch additional tasks in order to fetch the data faster and get up to speed. Fetcher writes all it fetches to the DFS, and when a data set is ready, the Polar launches an ingester job. That's another MapReduce job. It reads the files written to HDFS, and it writes them in H-file format, which will be easy for HBase to consume. Our partitioning, which the ingester does, and that's our partitioning in HBase 2, is by reverse host URL. So for example, http://search.yahoo.com/help will look like this. The reason we do that is for locality. Sites are often similar, and domains often have multiple sites who have similar content. For example, www.cnn.com is virtually identical to www.2.cnn.com, or other examples. So you get better compression and better performance when you do scans of entire domains if you represent the data this way. And the ingester creates files that we load into HBase using bulk loads. And I'll talk about that more soon. So, HBase. We have a cluster of 960 nodes running HBase. We set up one region server per node, which is standard. We have 5 column families, which is a trade-off between having a small number of column families, which is the recommended setup for HBase, because you want to keep the number of files small, and each column family has its own set of files. And optimizing for access patterns. Our data sets, our families are very different. We have one family, which is the actual HTML content from the web, which is very large. We have other families, which are metadata, which are very small. If you don't need the content, then you can only use the small data families and get better performance. Also, the data itself is different. And I don't want to go too much into that because it touches on the application, less on the infrastructures. 5 is where we converged as the optimum. We have 30 regions per node, so 30,000 regions total. This is also a trade-off between having a small number of regions and therefore a small number of files and a smaller load on the master. If you have too many regions, then startup time takes a long time because the master becomes a bottleneck. On the other hand, you don't want too small number of regions because then the overhead of things like compaction, and in case a region dies or a node dies, moving that region to another node is very high. So we converged on the number 30. There's nothing magical about this number. Similar numbers could probably work just as well. And we configured HBase for our large size. An interesting thing about our setup is that we only load data using bulk load. The common way of loading data to HBase is using put. In our case, bulk load was more natural for two reasons. One, latency isn't a concern. We get batches at roughly hourly intervals. So there was no reason to focus on puts that have second or sub-second latencies. On the other hand, throughput was critical for us. We get many terabytes of data every hour, and introducing this data into HBase one put at a time would have been very inefficient. We have made changes to bulk load. Minor compactions are typically triggered by put operations. Since we don't have put operations, then we changed bulk loads so that bulk loads triggered minor compactions. We set up major compactions. They're triggered externally, not really manually, by the poller every 10 days. So it keeps track of who had a major compaction when and triggers major compaction at this interval. We expire data based on timestamp per column separately. So every cell pretty much is expired based on its timestamp and also based on the number of versions. In our use case, we don't need to store multiple versions. We do that for efficiency, but we only ever look at the latest revision. And as soon as a cell acquires too many versions, we start expiring the old versions. The timestamp we used isn't the natural one, the time of ingestion. It's the time that the page was crawled, which helps us with consistency, because even if files arrive out of order, this guarantees that we always see the last version of the content. Our typical use case is full scans of the data. We also have a minor use case of random reads, which is very important and was one of the reasons we chose HBase, but our major use case would be full sequential reads through the data. So why did we choose HBase? It has many properties that are very good for our needs. It is very efficient on bulk loading data. Given that we're not using puts, but we're using bulk load, it can handle large amounts of data very efficiently. It runs MapReduce very efficiently. When you need full scans of the data, you can get very high throughputs using MapReduce. For our random read use case, it is also very high performance. You can do a lot of random reads, which you couldn't do, for example, if we chose Hadoop without HBase. You can easily add columns. A common expectation is that we will get new types of data from Microsoft over time, and also that we will do our own processing and enrich the content with additional pieces of metadata of our own. So the ability to add columns on the fly was important to us. Of course, it works on top of Hadoop, and Hadoop is very commonly deployed at Yahoo, so that was a strong plus for us. It has a good consistency model where since we can control the timestamp and we can control expiration, we can guarantee that we see the latest version of the data and it will never be overwritten by some data that happened to be written later. Also, just the mere fact that you can have multiple versions of the data, and this is important to understand, when you crawl the web, you typically refresh the pages. You have a certain size of your crawl corpus, and then You crawl a little bit of new pages, you throw out a little bit of old pages, and everything else is just refreshing the content of existing pages. So you have multiple versions of every page. HBase, out of the box, gives you the latest version of that page at very low cost and very high efficiency. And we can control expiration and keep our content at a fixed size. Along the way, we made some contributions to HBase. I mentioned the one where we trigger minor compactions on bulk load. Made a few other bulk load tweaks. When we entered the project, bulk load was somewhat of an afterthought. There was support only for one column at a time, so we added support for multiple columns. There was a separate tool for an initial bulk load for an empty table and for incremental bulk load for a table that already exists. So we merged them into one tool. We also wrote a few classes that help us with our data processing. When we scan the data, and since this is a large cluster, we have failures, of course, and we don't want to restart the job from scratch. So we added classes that allow us to easily restart the job when it fails and just pick up where it left off. We publish data sets that we mine from this HBase cluster onto other grids which are not running HBase. So to allow access to these data sets, we wrote classes that, even though the data is H file format, we wrote a class that makes it easily usable on clusters that are not running HBase. The bulk load enhancements are already shared with open source. They're already committed to HBase. The other classes haven't been updated yet, but they will be. Our experience with HBase, very easy to support. We have one operator that is operating these clusters plus a few other clusters, so he's doing this one part-time. We had great support from the community. When we were just starting on this project, we had many questions, and we raised them to the community, and we got back very fast, timely, and good responses. We saw, well, not really the latest version, but we had to run with version at least 0.90. The HBase master was pretty much rewritten to address scaling issues. Before that, a cluster of this size couldn't really run effectively, but since using this version, it runs very well, much faster. Startup times are a few minutes. Configuration is key, and our configuration has several interesting tweaks to address our specific setup. So the first one, small read cache. Since our major use case is full scans of the data rather than individual lookups, that is an important but minor use case, then we didn't really need a large read cache, and a large read cache takes up a lot of memory. The reason to really be careful with memory is because when you have basically garbage collection, minor planned garbage collection are fairly low weight, but if you have a major garbage collection, when you actually run out of memory, the Java process pretty much freezes, and we hit various timeouts that were hard to control. Two that come to mind, one is a zookeeper timeout. HBase uses zookeeper under the cover, but when garbage collection kicks in, you sometimes have cases where the region server doesn't talk with zookeeper for long enough time that the zookeeper timeout kicks in. Then zookeeper thinks that the region is down, but then the region comes back up and you have an inconsistent state. Another one is where the region server's DFS client times out. If it had some sort of DFS operation and then it goes into garbage collection, the operation would time out, then the region server would crash. So we set up small read cache, low swappability, all to conserve memory. We configured the large min block size for our larger column families. We didn't really do a lot of science around this. This was advice that we got from the community, and we implemented it, and it works well for us. We set up a long zookeeper timeout. This is a large cluster, 960 nodes, 30,000 regions. There are various zookeeper updates that happen. So we set a long timeout to avoid getting out of sync with zookeeper. We also set up large files to avoid as much as possible region splits. What we have observed is that every time we have a region split, we see a strong degradation in the performance of MapReduce jobs. So to avoid that as much as possible, we configured a very large file sizes. Moving on to the extruder on the top right there. The extruder kicks in once in a while on a schedule. It scans all the data in HBase. It selects a subset and copies the subset to one of the other grids at Yahoo. Interesting things about it is, one, it handles reliability and restartability using the classes that we have developed. You never want to restart a very large job. One side effect of splits is that we need to re-execute tasks when a split happens. Reason is, we have 30,000 regions in HBase, but we don't want to create 30,000 regions every time we dump a subset. So the extruder merges several regions into one file in HBase, in HDFS on the remote grids. This is to minimize the number of files that we create on these remote grids, because the number of files is always a limitation of name nodes. So this happens. And the filtering capabilities that it has are fairly rich. So you can say things like, I want all the data from Wikipedia that has been crawled in the last 24 hours and has this metadata, has a low spam score, has many links coming in, or any other such combination of metadata. Extruder kicks in, filters all the data that we have in this very large cache and creates a small subset just for you. Random reads. Another important use case, or several use cases actually. One is for search triage. So you get a certain result for a particular search and you don't really like what you see, so you want to go in and see what was the data used for this. Another is if you want to retrieve a small data set but fast. So you want to run the extruder when you want data set of millions of pages, but if you only want 1,000 pages and you don't want to wait hours for it, the time it takes for a full scan, then you can just go in and fetch 1,000 pages with random reads. And of course, for debugging, you just want to see what the system has. On the side, we have a processing cluster. So once in a while, low frequency. So we're talking here once a week, once a month, days. It goes in, it copies a large subset or even everything that we have inside HBase, and then it does heavy lifting processing. Things like graph algorithms, computing our version of PageRank or HostRank. And here I'm going to put in a shameless plug for Giraffe, which is software written by a member of the team, Avery, and he's giving a presentation on it later today in the other room. So attend that if you're interested. It's an infrastructure, a tool for running graph algorithms on Hadoop. Very efficient. And also we run various document enrichment processing, for example, aboutness, which is for every document figuring out a list of things on which the document speaks. Geotagging for every document, what are the locations that the document is about, classifications, is this spam, is this adult, is this a blog, is this a forum, etc. Plans for the future, increased volume. The web is growing. We expect the content that Bing is crawling to grow. We need to keep up with that. Customized dump. So currently what we support is filtering on various metadata fields that we compute. But in future, we would want to run arbitrary processing in order to select subsets. And incremental dumps, so things like an extrusion job that runs daily and only provides a delta, things that have changed since yesterday. And with that, questions.
So I have one question. So you said that you don't split regions at all, and so all the regions are pre-split and created upfront, right? But you also said that you you flip the URLs so that each URL goes to a certain region server or something. So don't you see one region server just filling up over time because there's a lot of activity on that URL?
Right, so the answer is twofold. One, we do not split at all. We try to minimize the splits. First, it's impossible to actually configure it such that there are no splits at all. You can just push them out further along with larger files, but we do have some splits. And yes, we do see some level of hotspots where we see some regions that are bigger than others, and then we do split them. We don't need them to be completely uniform, but we do want MapReduce jobs to run at a consistent speed, so we want the worst offenders to be not too far away from the average. So regions that become too big, we'll split. Yes?
You mentioned that you put the entire HTML page contents in.
Yes. I'll repeat the question. So we put all the HTML in our HBase. Is there not a concern about some pages being very large? So two things. One, I believe that even on the Bing side, they don't really crawl the content of pages if they are infinite, so to speak. They probably have a truncation somewhere, so they would be concerned about it. Certainly, in Yahoo's current crawler, we truncate documents. In web crawl cache, not so much. A region is very large, and a few tens of megabytes or a few hundred megabytes isn't that large when you're talking about a column family where each file is limited to many gigabytes. So yes, one file will be large, and then you'll have a minor compaction, and it'll be merged into an even larger file, and then a major compaction, and it's an even larger file. It's not a big concern. So the question is, why do we have two clusters, one for HBase and one for processing? It's a convenient separation of variables. We have the cluster that works with Microsoft, make sure that it keeps up with the data rate that's coming in, and does the processing that can be done inline, processing that is cheap enough to run inline. And then we have processing that can't be run inline. It's too expensive. It takes days and weeks to execute. You don't want those huge MapReduce jobs running on the same cluster that is sort of mission critical and feeding in data in real time. That data we want to come in a very consistent, reliable way, process, put into HBase, and feed out. And then in the background, we fill in without upsetting this cluster with massive jobs. Also, the jobs running on that other cluster tends to be resource intensive. They are running on the same hardware with 24 gigs of RAM and so on. They tend to saturate the hardware. So running them on the same nodes that are running HBase and trying to keep up with Microsoft would hurt both.